Ladies and gentlemen, good morning. Welcome to this session, GNF session dedicated to CERN's aerospace applications. Thank you for coming here. As you know, the theme of the Congress this year is involving everyone, and I think that this talk fits this theme very well, because my organization, CERN, the European Organization for Nuclear Research, is quite famous in the world for its fundamental physics achievements, but it is not very well known for its aerospace activities. Now, what you can see mirrored on the helmet of the astronauts in the picture behind me is the Large Hadron Collider, which is a big accelerator, 27 kilometers long, located 100 meters underground in Geneva. And of course, this is probably one of the most unlikely things that an astronaut will ever see up there in space, but it is a metaphor because there are many things that CERN can do to contribute to the aerospace community and also to benefit from the aerospace community. And this is what my talk is about. And I would like to thank GNF and the IAC for giving the opportunity for this talk. So I would like, if you agree, to start with a general presentation of CERN main mission. This is the movie, if you can please start it. So, as mentioned, CERN is an organization whose main focus is fundamental physics. We are an international organization with 22 member states based in Geneva, but our accelerator infrastructure goes across the border between Switzerland and France. Our machines are probably the biggest on Earth. It's a large accelerator infrastructure based on a number of accelerators which are chained one after the other. So everything starts from a bottle of hydrogen where electrons are stripped and the protons are accelerated in a linear accelerator first, then in circular accelerators, the proto-synchrotron, the super proto-synchrotron, and finally the Large Hadron Collider, where the particles collide in four different places, which are the main detector experiments we are operating. They are ATLAS, ALICE, CMS, and LHCb. And what we are doing basically is transforming energy into matter. We are trying to produce new particles and study them through our very complex detectors in order to find new physics. And as you can imagine, in this process, we are producing a huge amount of data that are handled, analyzed, processed through our infrastructure, and they are afterwards distributed all around the world for analysis in our partner institutions. So the technologies we are developing are mostly related to accelerators, detectors, and IT, information technology. And the result of our work is the finding of new particles that can confirm the standard model of physics or go behind it. The last one was the Higgs boson found in 2012 that went through the most important press release in the world. So this is the main mission of CERN: fundamental physics, high energy physics, particle physics. Now, if we go a little bit deeper into the mission of my group, which is the knowledge transfer group, we can get closer to the reason for I'm here today. So if the main mission of my organization is fundamental physics, in order to achieve its scientific goals, we have to develop technologies that can find applications to other fields. Probably the most famous technology developed at CERN by CERN that had a huge impact on the world is the World Wide Web. It was developed in 1989 by Tim Berners-Lee from CERN and has clearly changed the world. But there are a number of technologies that since then, even before, have been developed at CERN that can find application in many domains. The domain in which we are most active, apart from high energy physics, is medicine. We have a lot of applications to medicine, either therapy or diagnostics. So in terms of therapy, you have seen the images passing behind me. Hadron therapy was developed at CERN. We have largely contributed to this technology that allows direct treatment of cancer cells within the human body. But we have also other treatment technologies like isotopes for brachytherapy. And we are contributing to imaging through new MRI concepts, through positron electrotomography, innovative technologies, and X-ray through our Medipix technology. So medicine is clearly one of the domains in which we are more active. Now, the second one is aerospace, and we are getting closer to the core of this presentation. So we have a strategy for aerospace applications. We believe the synergies between high energy physics and space are very strong, because we are sharing the same challenges and constraints in terms, for instance, of radiation environment, of need to stand extreme temperature conditions, high vacuum, and most of all, reliability. We need to operate our detectors and our accelerators for long periods without human intervention, and it is clearly something we have in common with space. Now, we have technologies and facilities that through partnership with national institutions or industry can benefit the different subdomains of space. We believe we have a role to play in most of the domains where space is concerned, ranging from telecommunication to human spaceflight, Earth observation, navigation. First of all, space science is a domain in which we can contribute, and actually I have some examples here. The very first GNF session of this Congress was dedicated to the AMS experiment. It was given by Professor Battiston from the Italian Space Agency. AMS is probably the space project where CERN has contributed the most in the past, because it has been assembled at CERN, calibrated at CERN using our beams, and today the payload operation and control center is based on our premises in Prevessin. So this is the mission where the contribution from CERN has been more visible in the past, but there are a number of recognized experiments that are flying in space, and for which CERN is contributing in different ways. Basically, most of the space missions dedicated to astroparticle physics have been calibrated using the beams from CERN. This is the case of Nucleon, a Russian mission, CALET, a Japanese, and DAMP, a Chinese mission with the contribution of the University of Geneva. But we are supporting also in different ways other scientific missions like LISA Pathfinder from ESA and Euclid, where we are, for instance, trying to share our software for data handling that will probably be adopted by the ground segment of the Euclid mission. So space science is clearly a field in which we are active, but we have also some technological demonstrators, and this is a small project, Celesta, that we are particularly proud of, because it's probably the first fully CERN-driven nanosatellite. It's a CubeSat, a very simple CubeSat, 1 unit, 1 kilogram, 1 watt, 1 cube decimeter. The payload is provided by CERN, the platform by the University of Montpellier, and we have integrated the FLIO satellite program from the European Space Agency. And this mission is, of course, an educational mission, because there are a lot of students involved, either at CERN on the payload or at the University of Montpellier working on the platform. But it has also at least two important technological objectives. And the first one is to develop a miniaturized version of RADMON. RADMON is a radiation monitoring system that we have developed and deployed in our LHC tunnel. And we have have miniaturized it to make it very light and very low power consuming, so that it can easily be integrated in any CubeSat or larger mission. And we are also establishing an agreement with Aerospace from the Netherlands to provide this payload as primary or secondary payload to the CubeSat market. So the first technological mission of Celeste is validating in space Radmon technology, and the second one is related to our irradiation facility, CHARM. This is the one on the right of the screen. We have actually a lot of facilities at CERN that can be potentially used for the aerospace community. And CHARM is a very special one. It is an irradiation facility where we can produce a mixed field spectrum, which is very close to what we see actually in our accelerators, but also to what satellites see from low Earth to geostationary orbit. And it is a specific facility because the volume where the device can be tested is quite large. You can test a whole satellite in it, or alternatively batches of components like COTS components, and is very useful for screening COTS components, which is a trend in which space is going at the moment. This is not the only facility we have at CERN. We have other irradiation facilities, and one facility that can be relevant for space applications is VESPER, the Very Energetic Electron Facility for Space Planetary Exploratory Missions in harsh radiative environments. Basically, this is an electron accelerator that can accelerate electrons up to 200 megaelectron volt, which is a level of energy which is of interest for missions going to Jupiter, for instance, where the magnetic field of the planet accelerates electrons to those levels of energy, and there might be need of testing equipment going there. Now, apart from the facilities, there are a number of technologies that we are working on. We have developed in the past, we're going to develop in the future that can be of interest for space. Probably the most significant example I have is hybrid pixel detectors. They are used for science missions dedicated to astrophysics, and they are used in our detectors for particle physics. The Medipix family of detectors, in particular TimePix, is the one technology from CERN that has the longest flight experience, because it has been flying on European and American missions. In Europe, we have the University of Prague and the Institute of High Energy Physics of Prague, which is supporting the application of TimePix, for instance, on Probably satellite from ESA, the SATRAM instrument, or the VSUSat-1 satellite launched last year, part of the QB50 initiative. It is also flying an X-ray telescope based on TimePix. While on the American side, we have the University of Houston that is supporting applications like the radiation environment monitors on the ISS that are flying there since 2012. Several units have been flying there. You can see one in the picture in the cupola. And also on the test flight of Orion, we have a BIRD, a battery-independent radiation detector, which is integrating Medipix technology. And there are more examples that will be given if you are interested in a talk by Professor Pinsky this afternoon in a technical session. So please go there if you're interested. But apart from hybrid pixel detectors, we have many other technologies that can be of interest for space. We have other technologies for detectors, like monolithic active pixel sensor, also known as MAPS, and gas electron multipliers, also known as GEMS, that are currently being considered for space missions. We have technologies like radar electronics devices for power distributions, like DC-DC converters or high-speed links, optical transceivers that we are developing for our own applications, but they can be easily adapted to space. We are in the need of composite cryostats, which means tanks made of composite materials, because if weight is not a problem for us, transparency to particle is. So we need to develop composite tanks to be located in the inner part of our detectors, and is clearly something that can be of interest for the aerospace community as well. We are developing advanced materials for thermal control, either materials with very high thermal conductivity to evacuate heat fluxes in our collimators, or microchannel cooling devices that can be used at component level for regulating the temperature of electronics. And last but not least, we are developing high-temperature superconducting magnets that can be used in space, either for high-resolution astroparticle spectrometry or for radiation shielding on human spaceflight. Well, for active radiation shielding, it is a possible application. And also, we are developing a lot of software for big data management and analysis. Actually, this is not an exhaustive list of the technologies we are developing can be of interest for space. We could think about robotics as well. We could think about radio frequencies devices. But okay, the objective was not to be exhaustive. It was just to give some examples to show what the synergies are. Now, in order to transform these theoretical synergies into practical collaborations and projects, we need to cooperate, and we are cooperating since 2014 with the European Space Agency. We have a framework cooperation agreement with them that we are implementing at the moment. And we have been establishing also bilateral collaboration agreement with the French Space Agency CNES, with the Italian Space Agency ASI, and with the Swiss Space Center. And we are looking forward to extend this network to other national space agencies like DLR in Germany. And we would like also to consolidate our cooperation with industry because we believe this is essential in order to transform our needs and our expertise into real products for the market and for the benefits of all. So I hope the key message of this talk has been conveyed. Well, there are a lot of synergies between high-energy physics and space, and we are very much open to collaborate with space actors that are willing to work with us. So if you want to know more, please visit our website or contact me directly. And I think we have some time for questions. So thank you very much for your attention. If there are any questions, I think there are microphones in the room. If there are not, never mind. Please don't hesitate to contact me directly. I will be around at the conference for the next few days. And again, you have my contact details there. So thank you again for coming here this morning.